In this screencast, we're going to talk about valence bond theory and molecular orbital theory, which are two different ways, other than VSEPR, to think about bonding. Let us consider for a moment hydrogen sulfide, which looks an awful lot like, or you would think it would look an awful lot like water, in that it's got 4 groups of electrons. And you would expect the bond angle to be a little less than 109.5. VSEPR says that the hybridization would be sp3, the molecular geometry would be bent at a bond angle of 109.5. But the actual bond angle is 92.1. So we don't have 4 energetically equivalent hybrid orbitals. 109.5, 92.1 is nowhere near 109.5. So we have to come up with some other way of sort of explaining why hydrogen sulfide is nothing like that of water. So if we think about these 3p orbitals, this is their general shape. So here's a set of 3p orbitals. There's one orbital there, one orbital there, one orbital there. And here I have 2 unhybridized sort of atomic orbitals, each one half filled. So that means 2 of these 3p orbitals have 1 electron in them that are then overlapping with the 1s orbital of a hydrogen atom. 1 hydrogen overlaps with this 3p orbital, 1 hydrogen overlaps with this 3p orbital. And it doesn't matter what 3p orbitals they are, those 3p orbitals are actually 90 degrees to each other. And an actual bond angle of 92.1 sort of indicates that that's the actual bonding taking place. So in this case, it's not VSEPR bonding that's happening. There is no hybridization. We actually have something else, what we call valence bond theory, which is simpler than VSEPR, the VSEPR model. Valence bond theory simply says that a covalent bond is electron charge between 2 atomic orbitals. So the 1s orbital of hydrogen is overlapping with a 3p orbital in sulfur. Now, don't fret. Valence bond theory is just sort of like, oh, how do we explain other observed phenomena? Remember, the VSEPR model was what we used to explain why water had a bond angle of 104.5 and why methane has a bond angle of 109.5 and why we have those hybridization rules. And the VSEPR sort of model helps us to explain observed phenomenon. Now we have a way of explaining why hydrogen sulfide has a bond angle pretty close to 90 degrees, because it's probably just happening the atomic orbitals instead of hybridized orbitals. So that's valence bond theory. Now molecular orbital theory is much more complex. Let us review that hybridization is when you take atomic orbitals from one atom and form atomic hybrid orbitals. So when we talk about an sp3 set of hybrid orbitals around the carbon atom, those sp3 hybrid orbitals are attached to the carbon, an individual carbon atom or an individual oxygen atom in water. Molecular orbital theory, or sometimes referred to simply as MO theory, is slightly different in that we are going to combine atomic orbitals, so garden variety sp,d orbitals, of 2 different atoms together and form hybrid molecular orbitals. So it's still a hybrid orbital in that the orbitals that are formed are nothing like the atomic orbitals. They're sort of pieces and parts. But in this case, the key here is molecular orbitals, and that they are only associated with the molecule, not with the individual atoms like our VSEPR model did. So as with hybridization, when we made atomic hybrid orbitals, the number of hybrid orbitals that we make were a function of the number of atomic orbitals that we included. Same thing with molecular orbitals. The number of molecular orbitals is equal to the total number of atomic orbitals included. And we're going to talk about very, very simple molecules. We're going to just talk about very simple diatomics. So the simplest diatomic is that of hydrogen. Hydrogen atoms, the 2 1s orbitals from 2 individual atoms, come together to form 2 molecular orbitals. 2 atomic orbitals form 2 molecular orbitals. And these orbitals are given completely different names, but they're going to look familiar. The molecular hybrid orbitals, or molecular orbitals, MOs for hydrogen, are called sigma 1s and sigma 1s star. The sigma 1s is called a bonding orbital, and the sigma 1s star is called an antibonding orbital. And this is actually how it lines up. So this is what's sometimes referred to as an MO diagram. And the MO diagram will have the same sort of general structure, in that we put the atomic orbital of one element on one side and the atomic orbital of the other element on the other side. And so hydrogen has this has 1s orbital and this has 1s orbital. And our molecular orbitals form by matching them up. And we draw these little dotted lines to sort of say how they're attached. So what we've done is, this is the molecular orbitals for the hydrogen molecule. And this is how it's drawn. So the individual atoms, hydrogen, hydrogen, molecular orbitals, here's the molecular hydrogen. And again, these orbitals only exist as a molecule. So the sigma 1s are a bonding orbital, the sigma 1s star, an antibonding orbital. The 1s orbital is lower in energy than the 1s star. And now we have essentially a new Plinko board. So in our molecular orbitals, we have a total between the two atoms of 2 electrons. And so we drop those 2 electrons in the lowest energy orbital, and they fall into that bonding orbital. And so we have a bond. Having electrons in a bonding orbital is good. Having electrons in an antibonding orbital is bad. These 2 electrons then, we have electrons in a bonding orbital, which means that's sort of pro-bonding. And we only have electrons in the pro-bonding orbital. And there's our sort of 1s, sigma 1s. And yes, that is a sigma bond. And we had learned about sigma bond and pi bonds earlier when we were talking about multiple covalent bonds, that all single bonds are sigma bonds. This is actually where that sigma and pi come from. So as you can see, a sigma bonding molecular orbital, this is just sort of like what they actually look like. The sigma bonding molecular orbital encompasses both atoms. And so those 2 electrons are running around in that sort of molecular orbital. And an antibonding molecular orbital, which we can have electrons in, which we're going to talk about in a second, obviously looks very, very different in that there's actually a space in between where the electrons can't exist. Let us consider helium as a diatomic. So we would come together and make the same sort of marriage between the 2 1s orbitals. We would make a sigma 1s and a sigma 1s star orbital. And helium as a diatomic doesn't make any sense. I mean, we've never talked about a helium diatomic. Helium doesn't react. But let's sort of explain why using MO theory. So here are my 2 molecular orbitals, and I now have a total of 4 electrons to put in these 2 orbitals. So the first 2 electrons go in the sigma 1s, and that fills, and then I have 2 more, and I put 2 electrons in the sigma 1s star. So I have 2 electrons in the bonding orbital, and I have 2 electrons in the antibonding orbital. So I essentially have 2 electrons saying, yes, please bond, and I have 2 electrons saying, no, please don't bond. They sort of cancel each other out, which is why helium does not exist as a diatomic. So we can think of bond order as sort of, the concept of bond order that we learned a long time ago about covalent bonds is we have bond order in MO theory. That bond order is equal to 1/2 the number of electrons in a bonding orbital minus the number of electrons in a non-bonding orbital. If we go back to hydrogen, you'll notice if we just think of a hydrogen-hydrogen single bond, we would say that the bond order is 1. So here is hydrogen, and I have 2 electrons in a bonding orbital and no electrons in an antibonding orbital. So 2 electrons in the bonding orbital, 2 electrons in the bonding orbital minus all the electrons in the non-bonding orbital, since that's 0 in hydrogen, and there's 2 electrons in the bonding orbital, 1/2 of 2 is 1. So the bond order of hydrogen is 1, which totally makes sense. And in helium, we have 2 electrons in the bonding orbital, 2 electrons in an antibonding orbital. 2 minus 2 is 0. 1/2 of 0 is 0. So the bond order of helium as a diatomic is 0, which means it doesn't have a bond, which makes sense because helium doesn't exist as a diatomic. So if we were to form a hypothetical lithium diatomic species, we would have 2 electrons in the sigma 1s bonding, 2 electrons in the sigma 1s antibonding. Those can sort of, so there's 4 electrons there, 5, 6. The next 2 electrons go in the sigma 2s bonding orbital. Here's the MO diagram for lithium. So I have 1, 2, 3, 4 electrons in a bonding molecular orbital, and I have 1, 2 in antibonding molecular orbitals. So I take all the electrons in bonding orbitals, so that's these and these. That's 4 minus 2. So 4 minus 2 is 2. Divided by 2 means the bond order of the lithium diatomic is 1. Now, that's for real simple, just sigma bonding orbitals and sigma antibonding orbitals. It's a little bit different when we start getting to p orbitals. So let's consider boron for a moment. So the two 2s orbitals in boron form a sigma 2s and a sigma 2s star, just like they did in lithium in the previous slide. But they also form two sets of 2p orbitals combining to form another set of orbitals, a sigma 2p, a sigma 2p star, 2 pi 2p's, and 2 pi 2p stars. So we have pi bonding orbitals and pi antibonding orbitals. The little asterisk means antibonding. And here's sort of what they look like. And yes, these are starting to get ugly, and I know that. So here's a hypothetical boron molecule. And as you can see, we've got 2 electrons in a bonding the 1s come together to form a sigma 1s star. 2s come 2s star. And then here are the 1, 2, 3 2p's for this boron. 1, 2, 3 electrons of this boron. And they form sets. So there's the sigma 2p, the sigma 2p star. There's the pi 2p, and these are degenerate, same energy, pi 2p stars. And notice we have 2 electrons in the sort of this upper set, and a total of 2 electrons, and they go into the pi 2p here and here. So Hund's rule is still sort of satisfied, if you will, in that we have to fill the electrons half filled first. Let's look at another. So the pi orbitals are, here is the sigma bonding molecular orbital. So we have the 2p atomic orbitals come together and form a sigma molecular orbital, so a sigma bond. And then the pi orbitals, as we've talked about before when we were talking about multiple covalent bonds, the pi orbitals sort of build that highway between. So this is the bonding orbital, and this is the anti-bonding orbital of a 2p set of molecular orbitals. These are the 2p's. So let's consider a hypothetical carbon-carbon double bond. Or I'm sorry, a carbon-carbon bond. Here's our molecular orbital diagram, or hypothetical molecular orbital diagram. So we have the 1s combine, those sort of all cancel out. The 2s combine, sigma 2s, sigma 2s star, those all cancel out. Then we have 2 electrons in the 2p orbitals of this atomic carbon and 2 electrons in the 2p orbitals in this atomic carbon, following Hund's rule. We make our molecular orbitals, and there's 1, 2, 3, 4 electrons in our pi 2p orbitals. And a bond order in this case would be all the bonding orbitals, so all the electrons in bonding orbitals, so 1, 2, 3, 4, 5, 6, 7, 8, minus all the electrons in antibonding orbitals, 1, 2, 3, 4. 8 minus 4 is 4, divided by 2 is 2. So we get a bond order of 2. And you can almost see that because there's 2 electrons in that pi bond, 2 electrons in that pi bond. Let's go on to one that makes a little bit more sense that we're familiar with, that of nitrogen. So here's the molecular orbital diagram for nitrogen. 1s combine, sigma 1s star, all cancel out, same with the 2s's. There's our 3 electrons in the atomic nitrogen, 3 electrons in our atomic nitrogen, and when we make our MO diagram or start dropping them in, 1, 2, 3, 4, 5, 6, and when we go through and we calculate a bond order for this, we get a bond order of 3, a triple bond nitrogen, bond order of 3, and even before this whole discussion of molecular orbital theory, we'd say that it was 1 sigma and 2 pi, and there they are, 1 sigma and 2 pi. With fluorine, we go through, and now we actually start putting electrons in the antibonding orbitals. And sure enough, if we were to make, if we think about a fluorine bond, we know it's just a single bond, and there it is, 1 sigma bond. Because the pi bonds, the pi electrons, got 4 electrons in pi bonding orbitals and 4 electrons in antibonding orbitals. So they all sort of cancel each other out. So the only thing that's sort of left over are these 2 electrons in the sigma 2p bonding orbital, and that's our sigma bond. And then, of course, if we go on to neon, everything sort of cancels out because we start filling up all of our molecular orbitals, and all of our bonding orbitals and all of our anti-bonding orbitals are completely full, so they cancel each other out. So the bond order is 0.